lesson, you will get some basic knowledge about the trends in groundwater remediation technologies, focusing on chemical pollution. Traditionally, the remediation of groundwater polluted by chemical compounds has been carried out using pumping systems combined with water treatment plants located on site at ground surface, the so-called pump and treat systems. Over time, however, it has been widely verified that this approach entails numerous disadvantages, such as the need to withdraw large quantities of water from the underground reservoirs, the low concentrations of pollutants in the pumped flow due to significant dilution with the large volume of pumped water, the long time need to achieve the remediation target limits, the relevant energy costs for pumping, the installation and maintenance costs for the water treatment plant located on site. For these reasons, in the last 30 years, the so-called in-situ technologies have been developed and increasingly applied, where the dissolved contamination is removed from the aqueous flow directly into the subsurface without pumping groundwater out, activating the appropriate removal mechanism according to the characteristics of the pollutants and those of the aquifer. Among the characteristics of the pollutants, the chemical and chemical-physical properties, the biodegradability, as well as the starting concentrations and the objective of the remediation, place constraints on which mechanisms can in principle be used. The position where the contamination is located is also important, such as the depth from ground surface and more generally its distribution in the subsurface. As for the aquifer, the type of hydrogeological structure, its hydraulic conductivity, and groundwater velocity are usually of great importance. Among the in-situ technologies, particularly interesting are the so-called passive technology, that means technologies whose operation does not require constant use of energy. Among these, permeable reactive barriers and assisted bioremediation are to be mentioned as techniques already applied at full scale, while microbial electrochemical snorkels are still under investigation at lab scale. A permeable reactive barrier, or PRB, involves the emplacement into the excavated zone of the aquifer of a reactive filling material permeable to groundwater to intercept and treat the contaminants as the plume flows through under the influence of the natural hydraulic gradient. A wide range of materials are currently available. Some of them remove contaminants through non-destructive mechanisms, such as sorption or precipitation. Others through destructive mechanisms, such as abiotic or biological degradation. Sometimes concurrent mechanisms act in removing the pollutant or multi-layer system can be developed. More recently, suspensions of very fine materials have been injected into natural aquifers to spread them throughout a limited portion of the subsoil, resulting in the advantage of reactive barriers not needing soil excavation for the installation. Thanks to the flexibility in the removal mechanism and reactive materials, many kinds of pollutants can be treated, including chlorinated organic compounds, nitrates, hexavalent chromium, and heavy metals, polycyclic aromatic hydrocarbons, phenols, heterocyclic aromatic hydrocarbons, and novel issues for groundwater such as perfluorinated alkylated substances, also known as PFAS. The aim of assisted bioremediation is to promote the biological removal of pollutants by microorganisms already present in the subsoil, providing them with the necessary ingredients for their activity, and promoting the optimal environmental conditions for the process. Sometimes the limiting factor is oxygen, necessary to support aerobic degradation. Sometimes, vice versa, the optimal conditions are found in a strictly anaerobic environment, which can be promoted by providing a suitable organic substrate. In assisted aerobic bioremediation, oxygen is released into the aquifer thanks to the slow oxygen-releasing compounds, such as magnesium peroxide or calcium peroxide, which once poured into the saturated zone, hydrate with groundwater to release oxygen and transform into the hydroxides. Once released, oxygen moves into the saturated zone due to the transport mechanism of the porous medium over a time period typical for these mechanisms, let's say a few months. The injections can be repeated several times, depending on the overall oxygen demand, to remove the pollutant down to the target concentration. Typical contaminants that can be treated are petroleum hydrocarbons and non-halogenated organic compounds. In assisted anaerobic bioremediation, the added organic substrate is first fermented to hydrogen and low molecular weight fatty acids, in turn providing carbon and energy for anaerobic biodegradation of pollutants. The substrates therefore include low molecular weight fatty acids or carbohydrates as fast-releasing substrates, and vegetable oils, whey or chitin as raw-released substrates. Commercial products are also available, often combining fast and slow-releasing substrates. Assisted anaerobic bioremediation has been primarily used for remediation of chlorinated aliphatic hydrocarbons, but perchlorate and explosives can be treated as well. In a microbial electrochemical snorkel, a microbial anode is directly coupled with a biotic or abiotic cathode, as a single rod of graphite, steel, or carbon is exposed to two different redox environments. The snorkel does not require power, but works continuously at the maximum current sustainable by the system. Some of its operational challenges are still unsolved, such as the inability of controlling the electrode potential, the lack of sharp separation between the anodic zone and the cathodic zone, and the potential presence of oxygen in the anodic zone. Up to now, studies have focused on organic matter and nitrates removal. To conclude, the new trend in groundwater remediation from chemical pollutants consists in the use of passive in situ approaches with a view to increasing the sustainability of remediation interventions. The research and development of new technologies has made it possible to treat a wide variety of pollutants of concern for protection of water resources, ecosystem, and human health.